Hi, in this video, we will look at different types of motion. So this is going to be the first video of a chapter called as circular motion. This is the first chapter of your standard 12th physics textbook. So whenever you have an object which is moving in a straight line, so you have an object which is moving in a straight line, such a motion is called as a rectilinear motion. Take an example, you have a car and you have a straight road. So this object is going to move in a straight line. So whenever an object moves in a straight line, it's called as rectilinear motion. And whenever the object is moving in a curved path, now take an example like this, you have a car moving on this curved path, or this could be like a hill or a ghat. Whenever you go to maybe a hill station, you get a ghat in between. So there you are driving on curved roads. So whenever an object is moving on a curved path, such a motion is called as a curvilinear motion. So there are two types of motion. Motion in a straight line called as rectilinear motion, and motion in a curved path which is called as curvilinear motion. We will understand what you mean by circular motion. So whenever your particle moves along the circumference or a boundary of a circle, the motion is called as a circular motion. So it's moving along the circumference or the boundary of the circle. Let us understand this. Let's say you can see this giant wheel. Now if you see a human out here, a human is going to move along the circumference or the boundary of the circle. So this guy is going to move along the circumference or the boundary of the circle. So such a motion for this individual is going to be circular motion. So you have a person who's sitting and he's performing which motion? Circular motion, because he is actually moving along the boundary of this circle. Now if you consider the entire giant wheel, I am not considering the person sitting here, I am rather considering the entire giant wheel. Now in that case, the motion is a rotational motion. So you have a rotation of a body. So this entire body is rotating along this point which is called as the axis. So the motion for the entire giant wheel is going to be rotational motion, but the motion for the person sitting here is going to be circular motion. I again repeat the difference. Whenever a person is moving along the circumference basically means boundary of the circle. So whenever a person is moving along the circumference, the motion is said to be circular. Whenever the entire body is rotating, now this body is not moving, it is just rotating about a fixed point, and that fixed point is the axis. This entire giant wheel is not moving, it is just rotating about a fixed point, and that point is called as the axis. So the motion for the entire giant wheel is going to be rotational motion. We will understand a concept called as radius vector in circular motion. To understand this, we should first revise what are scalars and vectors. In physics, any quantity which you can measure is basically called a physical quantity. So anything which you can measure is a physical quantity, and we classify a physical quantity into two types, depending upon what it takes to completely describe a physical quantity. So if I want a complete description of any physical quantity, I require two things. The first thing, I require the number, which is technically called as the magnitude, plus the unit. For example, I say the mass. The mass of a pencil box is 5 grams. So 5 is that number which we want. That number is called as magnitude, and this grams is a unit. Now whenever for any physical quantity, a magnitude and a unit gives its complete description, it's called as a scalar. So in this case, a magnitude plus a unit gives a complete description. Therefore, you call this mass as a scalar. But there are certain physical quantities which require the number, that's the magnitude, unit plus the direction. Such quantities which require magnitude, unit plus directions are called as vectors. Let's take an example to understand this. Let's say I have a small box and I'm applying a force of 5 Newton. Now 5 is that number I was talking about. Newton is the unit. So I have the number and the unit. But still this information is incomplete. Why? Because if I apply the force like this as shown in the figure, the object is going to move towards the right. If I change the direction of the force and I apply the force from the top, the object is going to move at the bottom. So the direction in which the force is applied matters. Therefore, for complete description of force, I require 3 things: magnitude, unit, plus directions. So any physical quantity which requires a magnitude unit for complete description is called as a scalar, and which requires magnitude unit plus direction for complete description is called as a vector. Now, how do you denote a vector? If you want to denote a vector, you require minimum 2 points. The first point is at the bottom, which is called as the tail, and the second point is at the top, which is called as the head. So for denotion of a vector, generally you require how many points? 2, tail and head. Now, we always denote a vector using capital letters. So we write capital AB bar. This A is your tail or your starting point. This B is your head or your ending point. Now, if I fix any one point, let's say I fix this tail. Fix means I'm not going to change it. I'm going to keep it fixed. So if I keep one point fixed, that is origin, then the same vector can be called as a position vector. So what is a position vector? A position vector is nothing but a vector in which your one point is fixed, and that fixed point is called as the origin. So you take up an example, the same vector. Now I have the origin tail and I'm fixing the tail to be what? Origin. So I am only going to change one point here, that is A. So whenever I am fixing one point and I am only changing one point, I call it a position vector. If I change both the points, I change the tail as well as the head, then I call it just a vector. So here one point is fixed. To denote just a vector, we used capital letters. So here also we will use either capital letters OA bar. Now why I am using O? Because this is always going to be fixed. So I could have a OA bar here. If I take this point and I shift it here, I will have a OB bar. I again repeat, if I take this point and I shift it here, I will have a OB bar. So here my tail is fixed. I have what? OA bar. Either I can use 2 capital letters or I can use the small letter. And this letter is only going to denote that point that is going to change. In this case, our A is going to change. So this small a is written, which basically denotes only that point which is going to change. So this is how do you denote a position vector. And remember, for position vector, the point, if you are using a single point to denote a position vector, it should be small letters. So only small letters should be used to denote a position vector. Now understand a radius vector. Now what is a radius vector? Let's say initially your particle, a car, which in this case is a particle, is performing circular motion. So this car is currently at point A. Now the starting point is the center, which is O. Can you see that? The starting point is the center, which is O. Now is this starting point going to change? No. Even if the object is going to move, the starting point will remain the same. So your ending point, which is the position of the particle A. So there are 2 things for you to understand. One is your starting point, which is O, the center, and one is your ending point, which is the position of the particle. Now let's say the particle moves to another point B. So now the particle has moved to another point B. My initial point is still the same, which is the center. But my ending point or final point has changed, which has now become B. So I am going to call a radius vector a position vector. Why I am calling it a position vector? Because the initial point of that vector is fixed, and that was O, and the final point kept on changing. Now we have studied one thing: a line is made up of infinite number of points. Similarly, I can say this curve is also made up of infinite number of points. So if I say this curve is made up of infinite number of points, I can say I can have infinite radius vectors depending upon the position of the particle. I again repeat, a line is made up of infinite number of points. Therefore, I can say a curve is also made up of infinite number of points. And at any point, I can mark the position. Therefore, I can say I have infinite radius vectors depending upon the position of particles. Now, radius vector, radius is like length. Therefore, the unit is in meter. When it comes to dimension, mass is going to be 0. Length, its meters, is going to be 1. Time is going to be 0. We will discuss what are the quantities which you require to completely describe circular motion. So let us understand a few basic fundamentals. What do you mean by the word linear displacement? First of all, linear basically means in a straight line, and displacement means shortest distance between any 2 points. Let me make this statement very clear. Now let's say a car moves from A to B. So the car is moving in the downward direction. Now the car is going to move right. So if the car is going to move right, I say it reaches at this point C. So the car started from A, first went to point B, then went to point C. So the starting point of the car was A and the ending point of the car was C. So the actual path followed by the car was ABC. The actual path which the car follows is called as the distance. So distance is this actual path which the car is following. So this ABC is basically called as what? Distance. Now the shortest distance. Can I say if I draw a line between A and C, which we call it as the hypotenuse, it's going to be the shortest distance. So this shortest distance between any 2 points is called as a linear displacement. So a linear displacement is basically a shortest distance between the 2 points, which in this case, if I draw a line from A to C, this is called as the linear displacement, but the actual path followed by the car was A to B, and from B it went to C. So that actual path followed by the car is basically called as the distance. Now, the symbol for linear displacement is S, remember that. And the unit, since it is distance, or it's basically the shortest distance, the unit is in meters. Now let's understand circular motion. Let's say the car which was at point A is moving along a circular path and it reaches point B. A car which is at point A is moving along a circular path and it reaches point B. So two things are important for you to understand here. Point number one, you need 2 displacements for complete description of this motion. So when your car is moving from A to B in a circle, you need 2 displacements for complete description. The first thing is the actual distance traveled from A to B. Can you see that in red? Now this distance or this displacement from A to B is called as linear displacement. So this red is basically the linear displacement and the symbol for that is S. At the same time, can I say the angle at the center also changed by some value? So this angle at the center is also changed by some value, and if we want to describe circular motion, we also need to describe the angle which has changed. So therefore, I will say the angle theta is called as the angular displacement. So there were two displacements to describe circular motion. The first one was linear displacement. The second one was an angular displacement. Now, every physical quantity is a vector or not. Now, if I want to check a physical quantity is a vector or not, I generally say it should have magnitude, unit, and direction. But that is not always right. These three things are not sufficient to take a conclusion that the physical quantity is a vector. So today I'm going to teach you how do you decide whether a physical quantity is a vector or not. So let's consider angular displacement. Let's consider two values of angular displacement. One is called as a finite, one is called as an infinite semal or instantaneous. Finite basically means large value of angles. Let's say 35 degree. So 35 degree is called as a finite value, and the finite value for angular displacement considered as 35 degree. A very small value for theta is like infinite semal, where theta is considered to be 0.67 degrees. Now this is a very small value. So a small value can be called as infinite semal, or you can either call it instantaneous. Now I need to check both of them are displacements, angular displacements. So I will assume both of them to be vectors. And then I will decide which is a true vector, which is vector in real sense. So generally what we say that it should have magnitude plus direction and a unit. So obviously it's an angle, it's got a unit radian, it's got a number 35, a unit degree, plus a direction, clockwise or anti-clockwise. So therefore I would call this a vector. I again repeat, theta has got a number 35 plus a unit degree, plus it's got direction. It could be clockwise or anti-clockwise. So I will call it a vector. But I told you that is not the right way to decide whether a physical quantity is a vector or not. We check two laws of vectors. The first law we check is called as the commutative law. Now, this finite vector is not going to obey the commutative law. When I say it's not going to obey, means the commutative law is not valid. So first of all, understand what is a commutative law. A commutative law basically means order does not matter. So whether I write A bar plus B bar and I interchange the order and I write B bar plus A bar, it still means the same. If that was the case, I say it will be a vector because it obeys the commutative law. But a finite value, it does not obey the commutative law. Therefore, I put a non-equal to sign. So therefore, I will say a finite vector is not a vector in real sense because it is not obeying the commutative law. Second law I want to talk about is the associative law. The associative law basically says grouping does not matter. So however you start grouping, that's not going to matter. Let's understand. Let's say you have three vectors, A bar plus B bar plus C bar. So I've written it twice. Now if you remember your older standards, we have studied something called as the bed mass rule, where you always start with brackets. In mathematics, you always evaluate your brackets first. So here, if I write the bracket for A plus B, A bar plus B bar, I am evaluating this bracket first and then I am coming to this bracket C bar. So first I am evaluating A bar plus B bar and then I am coming to C bar. In this case, I am first evaluating B bar plus C bar and then I am adding A bar. So the grouping is different, right? This is called as the associative law. But a finite or a large value of angular displacement does not obey the associative law. Therefore, I am not going to put an equal to sign. I am going to put a not equal to sign. So finite angular displacement is not a vector in real sense because it is not obeying your commutative law and associative law. Let us take up an infinite semal or a very small vector. They obey the commutative law. So we all know commutative law basically means order change. So my A bar plus B bar, if I interchange it, it becomes B bar plus A bar. Still I am going to put an equal to sign because an infinite semal vector is going to obey this. The second law is called as the associative law. associative law is also going to be obeyed by the infinitesimal vector, and the associative law says grouping does not matter. Now when I say grouping does not matter, basically it means if I write a bar plus b bar plus c bar, I just told you we use the bedmass rule where the brackets are evaluated first. So if I write on the left hand side of the equal to, carefully see, on the left hand side of the equal to, I write a bar and b bar first. So I'm evaluating a bar and b bar first, and then I'm adding the answer of a bar and b bar to c bar. On the right hand side, I'm adding a bar plus c bar first. So when I add a bar plus c bar first, and then the answer of a bar plus c bar is added to b bar. Still, if I get the same answer, it means it obeys the law. So I'm going to get the same answer, and I'm going to say associative law is obeyed only in case of infinitesimal vectors. And the commutative law is also obeyed only in the case of infinitesimal vectors. So understand one thing, an infinitesimal vector is called as a true vector because it's got magnitude, unit, direction, plus it obeys the associative law and the commutative law of vector addition. Whereas a finite vector does not obey the commutative law and associative law of vector addition. Therefore, it is going to be called as a pseudo vector. So remember, we are going to now, from now onwards, only consider instantaneous vectors. So from now onwards, we are going to only consider very small or instantaneous vectors. Now understand two important rules. One is called as a right hand screw rule. So can you see the screw? Now this screw, if I start rotating in the clockwise direction, it's going to perform circular motion. So when I rotate the screw in the clockwise direction, it is going to perform circular motion. The screw is going to advance downwards. So the screw is going to advance downwards. So whenever we're performing clockwise motion on a screw, it advances downwards. It helps us to predict the direction. And this rule is called as the right hand screw rule. Similarly, if I take the screw and instead of rotating it clockwise, I rotate it in the anti-clockwise direction. I'm going to change the rotation of the screw in the anti-clockwise direction. Then the screw is going to come out, and I'm going to say the screw advances upwards. So again, these two rules of the screw help us to predict the direction. Therefore, it's called as the right hand screw rule. Now, what's a right hand rule? See, you take up a wire and you hold it in your right hand and you curl your fingers. Just imagine this to be a wire. I am rolling my right hand to it and I am curling my fingers. Can you see this? My fingers are like this. So this fingers are in the anti-clockwise direction and my thumb is pointing upwards. These fingers are in the anti-clockwise direction and my thumb is pointing upwards. So you have the fingers movement basically tells you the circular motion is anti-clockwise and the direction is given by the thumb. So again, this is another rule which helps us to find out the direction. Now the direction of an infinitesimal angular displacement. Remember, we are only going to talk about instantaneous angular displacement from now onwards because an instantaneous angular displacement is a true vector as it has got magnitude plus direction plus a unit. At the same time, it's going to obey the commutative law and the associative law of vector addition. And the direction of this infinitesimal angular displacement is given by right hand screw rule or right hand rule because both of them at the end of the day give you the same direction. So there are two ways. If your circular motion is anti-clockwise, you will consider your direction to be positive, and if it is clockwise, you would consider your direction to be negative. So let's have a circular motion. So the direction of infinite angular displacement is perpendicular to the plane of the circle and upwards. So remember, this is perpendicular to the plane of the circle and upwards when your direction is anti-clockwise. So I would draw it like this. This is an anti-clockwise circular motion, and this is like an axis which is coming out, and this is the direction of infinite semal angular displacement, which is perpendicular to the plane of the circle and upwards. Let's talk about clockwise direction. So for clockwise, you will take negative. It's perpendicular to the plane of the circle and downwards. So the direction for clockwise circular motion is perpendicular to the plane of the circle and downwards. So it's something like this. This is perpendicular to the plane of the circle and it's directed downwards. It's perpendicular to the plane of the circle and it is directed downwards. So this is basically the direction of infinite semal angular displacement. Now, just remember one thing, the infinite semal angular displacement, the unit for this is radian, and it's dimensionless because a radian never comes under length, mass or time. And can you see this is like an axis which is coming outside? So an infinite semal angular displacement is called as the axial vector as it is directed like an axis. So remember, an infinite semal angular displacement is called as an axial vector as it is directed like an axis.